Okay, this is about EC Calc and the secondary waves. I get the feeling that it's hard to wrap your head around the idea of the secondary waves. It's hard enough to wrap your head around the idea of the primary waves. So it's a learning process. And the more you go over it, the more it'll seep in, the more it'll become second nature to you. So if you find it mind-bending, just keep your nose to the grindstone. It'll bend your mind until your mind conforms to the truth. So right now we're looking at the primary waves, the diffuser wave and the baffle wave. And the latest EC Calc is able to incorporate the secondary waves. If you look at this little green graph right here, there's a little positive hump right here, there's a little positive hump right there, causes that positive right there. This little negative causes this to dip down a little negative a little bit faster. So that's pretty minor, but the latest improvement on the program has been to incorporate the effects of the secondary waves on the exhaust, because everything keys off the exhaust. On sheet 4, it tells you right here what the estimated exhaust pulse pressure is. Okay, if you look at this, it's a simple little drawing. It's showing the exhaust wave exiting or being created by the exit of the exhaust from the cylinder into the exhaust port, and it's heading down the exhaust port, and it could be that a second generation diffuser wave from the cycle. Yeah, it could be from the previous cycle or the same cycle. When it comes, well, actually that's not true. Let me make sure I know what I'm talking about here. Okay, that's more like 6D. Okay. Well, it's late and I've been working all day long and I'm tired. So this should say 6th generation, which is from the previous cycle. So as it comes back, if it comes back right when this exhaust wave is beginning to form, it is actually on top of it, and it's a negative pressure, and the exhaust wave is a positive pressure, so it lowers the exhaust wave. And as you lower that exhaust wave, it also lowers the diffuser wave and the baffle wave. So it becomes where it reduces the boost that is created by the pipe. So it's very, very important. And I'm glad it's finally incorporated in this version. And how I've done that is when it's pretty close to the middle of the exhaust wave, reducing its peak, it shows right here for each of these RPM what the result is of whether or not it's there or not. If nothing's there, it's going to be 1, which means it's not going to increase or decrease. When you multiply anything by 1, you still have the same number. This showing right here at 9,500 RPM, the wave has been reduced to 59%. And here at 7,000 RPM, the wave is increased by 11%. So these are multiplication factors for the final numbers that are determining the pipe power in this graph here. But it's all automatic. You don't have to worry about doing it or even completely understanding it. all you got to know is what this little button right here is for. That button is to be pressed, and when you press it, all the calculations happen and the graph is displayed. And this is a near perfect graph, which is really hard to get with all these waves bouncing around causing interference. So when you, let me show you, not that, where is it? There it is. On sheet 1 we've got these two charts right here, or two graphs. The first one shows in this zone in the orange. This line out here is the timing of transfer closing, and this is the timing of exhaust closing relative to the RPM. This is a 3,000 RPM range. So, and this is the peak. This is the end of pipe power band RPM. So what it's showing is that zone, which is when there's a positive pressure there, it benefits pipe power. So you hope to have the baffle wave happening during that zone. And when that pressure is reduced, or even becomes negative, it kills the power. So what we have here, and the green right here, is the 3D wave. What does 3D mean? It means the third generation of the diffuser wave, which means the exhaust wave came, it hit the diffuser, it returned a suction wave. That's the first generation of the diffuser wave. And it can hit the piston, or it can go into the cylinder, hit the far wall, and come back out and create another diffuser wave. That's 2D, the second generation. The same thing happens, that's 3D. So this program calculates all the way out to 7D, because that's the maximum at which it really affects the power band. So this is 3D. This reddish zone is 2D. This gray zone is 3B, which is a positive pressure. These two are negative pressures. Like I said right here, you want the positive pressure. And the gray zone is the third generation of the baffle wave from the previous cycle. This black line out here is bottom dead center. So this shows the timing from bottom dead center to, am I saying that right? Yeah, bottom dead center to transfer closing. So in between this line and this line, you want negative, which is what you're getting right here from 2D. But right here you're getting positive from 3B. So it's always a crazy mix. And we're trying to make some sense out of it. I am, anyway. I hope you can follow my mental pathway here. In this chart right here, we've got in the orange zone right here the exhaust wave. The 0 is when exhaust port opens, and so you've got a certain amount of time for that wave to happen coming out of the exhaust port. And then you've got these waves crossing it. We've got two positive, which can increase the positive pressure of the exhaust pulse. This is positive, and this negative right here is positive, which this is 2B and this is 3B. But usually they happen at just a little bit at the beginning and a little bit at the end, so they really don't much figure into the equation. What we're mostly concerned about is the diffuser waves, which can subtract from the exhaust pulse pressure. So in red here, we've got 5D. In green, we've got 6D. And gray, we've got 7D. Okay. The zone at which they start to really have impact is like right here. This is 8,000, this is 9,000. So this line right here is 8,500 RPM. And as you can see, that green zone is just now at the halfway mark between the beginning of the exhaust pulse and the end of the exhaust pulse. So from there until the other side of it is at that halfway mark, about right there, which is about 250 RPM. So for about 750 RPM, you've got that molesting the exhaust pulse, bothering, reducing its strength. And we can see that right here in my notes of 6D. Exhaust pulse reduced by 6D from 8,500 to 90, well, a little bit before 9,500, about right here, about 9,350. I need to change that. So I was researching to find out where I should make these land, because these are controlled. Where these three diffuser waves land on the exhaust pulse is controlled by the header length. The longer the header, the longer these three are up on the graph. So we start at 315 header, and let's look what we have with a 355 header. You see the green is no longer in the middle like it was here. It's higher. And so you basically have gotten rid of 7D's influence completely. So now we've got 6D and we've got 5D to worry about. So that's how you play with those. The baffle length, I mean the distance from the piston, needs to be a certain amount to synchronize with the exhaust port for a certain peak RPM. So consider the distance from here to the piston is set. Once you find that out, you won't vary it by more than plus or minus 10 millimeters. And 10 millimeters is about 0.3 inches. So the lengths we have to play with are the header, diffuser, and belly. I like to look at it in mostly I look at it as being header and diffuser, because belly is controlling the overlap of the diffuser and the baffle wave. When you have the right length of belly, you've got a nice linear progression here between the two. So by the guidance here, it sets the correct overlap, the right length of the belly. So what you can do is you can lengthen the header or shorten the diffuser, or shorten the header and lengthen the diffuser by the same amount to keep that baffle the same distance from the piston. So that's what I have done on these graphs that I recorded. So when I say, well, right here you can see all the specs: 315 header, 340 diffuser, 90 belly, and 220 baffle. So that's a pretty funky looking wave. I don't really like that. So I increased the header length. I like this a lot better, but it's a little bit all, that's a little bit weird, coming on so strong at the beginning. Okay, so I went 20 millimeters more, and voila, the perfect power band. And just to see what would happen, see right here you've got the 6D. Let's say the middle of that exhaust pulse is about right there. So you've got 6D just past the middle of the power band. And here you got 6D just before the middle of the power band. So I wanted to see what it would be like with 6D right in the middle of the power band. And I did that here. And it gave me a strange result. So I didn't like that. So looking at the chart here, we used to go by this chart before I knew how to calculate for the generational waves, the secondary waves on the exhaust pulse. So if you look here at 3,000 RPM below the peak, we've got the end of 6D happening at exhaust opening. So now on sheet 1, that's what this number does. It helps you get the right header length so that you've got that. Which you can see we just lost it here. This should be right here. And see how far off it went just by 20 millimeters? Go back, and now look, there it is. Okay, so that's what I've got this tuned to. This belly is tuned to a certain amount of overlap between the waves. And then the diffuser makes up the difference to make sure that the total length to the baffle is correct to get the peak RPM here. So this is interesting, but now my focus is a lot right here. But this is important too. It's all there, all mixing together. So you can see on my notes here, this is saying the TC-EC zone has been reduced by 2D. And yeah. So that's really all you need to know, is that this will be your guidance. And then on sheet 3, it's interesting to note, just looking at the green graph, where the secondary waves are, how it's affecting the primary waves. So when you run the autograph, it will display the power band. And if you don't like it, change it by 20 millimeters or even 10 millimeters. Just go back to sheet 1. Increase this length by 10, decrease this length by 10 or 20. And then go back to sheet 3 and click autograph. You don't even have to deal with sheet 2, because when you did that, when sheet 2 is set here on automatic and 3 cone, whatever distance you put in for the cone length on sheet 1, which is right here, will be used on sheet 2 to generate the dimensions, and then the numbers are calculated. They're put over here and automatically transferred to sheet 3. So it's all automatic. And once you set the baffle distance, those numbers are here, and it's all automatic. So you enter all the numbers, you go to sheet 3, you click on this, you look at how the power band is. If you don't like it, you might want to take a note of these numbers, and maybe even, well, ideal would be to take a screenshot, but a lot of people don't know how to do that, and it's not that easy on Windows. I think you need a separate program to do that on Windows, and there are free ones on the internet to use. But you could just note down these numbers and the header length, and then just go from there. Change the header length on sheet 1, come back to sheet 3, graph it, take note of the numbers, go back to sheet 1, change it again. It's a process of maybe 4 different tries before you'll decide on which power band you like most. Sometimes, actually in the very beginning, you might want to take note here. Like in this case, I wanted the end of pipe power band to be at 10,000, but I've undershot that by 9,500. Not because sheet 1 is screwy, but because it's hard to predict the effects of the secondary waves on changing that end of pipe power band RPM. So in this case, automatically you'd want to decrease the header length without changing the diffuser length to shift the whole power band up 500 RPM, which might need probably about 30 millimeters on the header. So that is it, my friends. And it's just also another point that's important to note is how the secondary waves affect the wave shape of the power band, and how these cheap ass programs, they're either free or like $25, do not incorporate the secondary waves, so they can't tell you what shape the power band is going to be and whether or not you've lost overall power or not. Having a wave simulator making use of the secondary waves in both of these manners here is important. Okay, that's all for now. Thanks for watching.